Today we will be going over chapter 8. We will start doing some different reactions, for instance with potassium manganate, or some freaky reactions, and go over Markovnikov's rule, and hopefully we could cover everything within this video, right? So the first question asks, what happens when we do a Markovnikov addition to HI on 2-methyl-2-butene? So what I would do first is to draw out 2-methyl-2-butene. So butene means that there's 4 carbons and one of them has a double bond, so we're going to draw out 4 carbons. Alright, now we have to put our double bond somewhere, and it says to put on the second carbon. So we put 1, 2, 3, so I'm going to put it between 2 and 3 right here, right? And then we have a 2-methyl. We have a 2-methyl on the second carbon. So what happens if I try to react it with HI? Well, what happens here is that the bond breaks, releasing this hydrogen, and this double bond is so electronegative that it can act as a base, right? So it can accept this hydrogen. So we pick up this hydrogen, and what we have now is this methyl group right here, and a positive carbocation. Positive carbocation right here. So right there, because actually whenever it forms, the hydrogen actually gets placed over here. So we can draw out our hydrogen right here. So we have 2 hydrogens, so there was already a hydrogen right there, and then when this double bond picked him up, right, we put another hydrogen. So here we are. So there is a formation at the carbocation at carbon 2. Why is it not carbon 3? Well, it's not carbon 3 because already there is no hydrogen on the second carbon. It's just a methyl group. So carbon right here is this carbon has 1, 2, 3, 4 bonds. So it only has a methyl group, not a hydrogen. This carbon right here has 1, 2, 3. So there was an implied hydrogen already. So if I break this double bond, the hydrogen is going to have a buddy. And so he's going to have 2 hydrogens now, you see? And this one is partially empty, so that's why it's positive, okay? So there is a positive carbocation. Now, it didn't tell me to do the reaction, but if I were to do the reaction, I would have the I right here. So the I would be bonded right there, iodine. And that's Markovnikov's rule. So, well, I'll talk about Markovnikov's rule later. Now we have to do methylcyclohexane with HCl, so it sounds like a Markovnikov's rule problem. So here's cyclohexane, and that's not a good cyclomolecule, right? Okay, so I really can't draw today, my gosh, right? Okay, so that's the cyclohexane, and we need cyclohexene, so we could just put a double bond anywhere, and we could put a methyl group. Okay, so now we have HI, or HCl, right? So this double bond breaks, releasing this hydrogen. The bond breaks and picks up that hydrogen, right? And where do I put this hydrogen? Well, Markovnikov's rule states that whichever is, well, I don't really like that definition. Hold on. I prefer this way. So if you're just working with like a basic molecule, for instance, a cyclohexene, well, you're going to notice that you have some hydrogens already. So in this bond right here, we're going to be reacting with this one, this carbon, and that carbon, okay? So this carbon and this carbon, right? So this carbon has 1, 2, 3 bonds to it. So that means that there's an implied hydrogen. This carbon has 1, 2, 3, 4 bonds attached to it. So there is no hydrogen, okay? There are not any hydrogens. So this hydrogen wants to be with his buddy. He wants to be with more hydrogens because he's partially positive, right? He's partially positive. And so the way I like to think about it is that hydrogen goes with hydrogen, right? So I should be expecting that this carbon gets this hydrogen, right? And so we form a carbocation at this part. And notice that I'm right because we have a tertiary carbocation if we do that. So let me redraw the molecule so it's not messy and that you can see what I'm doing right here. Okay, so we have some implied hydrogens, right? And then we have a carbocation. That's a tertiary because it's right here, 1, 2, 3. And so now notice that this hydrogen was partially positive, so now this guy, this chlorine, is partially negative. And so what do you know about partially negative? Well, negatives goes with positives, and so he's gonna connect over there. And so you should be having this molecule, right? Of course, this could be like stereochemistry, right? But in this case, it's not. Like the answer choice shows that it's not any stereochemistry, right? So for instance, right here, why do you have a double bond? We break the double bond during a dehydrohalogenation or something, or actually hydrohalogenation, right? Because we're actually putting hydrogen, we're putting halogens in it. So you shouldn't have a double bond, right? Okay, so that's wrong. Your chlorine should be with the methyl on the same carbon, so that's wrong as well. That one's right. This one's on a different carbon completely. And what happened to your methyl group? That's weird, right? So number 3 would be right. Number 3 would be right. Okay? Cool. And as we go along, the questions will uncover Markovnikov even more, okay? So don't worry about it. We'll just we'll cover it as we go along, right? So over here, yada yada, same thing, right? So we have HBr, bond breaks, releasing this hydrogen. This double bond picks this hydrogen up, right? It picks them up, okay? So we have 1, 2, 3, 4, 5, and then a methyl and a hydride, or hydrogen, okay? Yeah. So it's true that this okay, let me kind of like magnify this, I guess. So already over here we have a hydrogen, right? That's implied, and then we have 2 hydrogens, right? And so hydrogen wants to go with more hydrogens. So we put our this guy, we put him over here, right? And that forms a carbocation, which is secondary. But is there a way that I can make a tertiary carbocation? Is that possible? Well, you know, I think it is possible, because what happens if I put this hydrogen over here? That's called a hydride shift, right? If I put the methyl over there, I will still get a secondary carbocation, and that doesn't make any sense. So when in doubt, if you get the same products, for instance, if you started with a secondary carbocation and you do a shift and you get another secondary carbocation, try doing a hydride shift, or try doing a methyl shift if you did a hydride shift, right? Do the other, is what I'm trying to say. So if we do that, we end up getting this. Okay, so that turns out to be a tertiary carbocation, right? So that's 1, 2, and 3. The methyl in this case counts as a carbon, right? Okay, so that's a tertiary carbocation. And now this bromine is going to be very attracted to this methyl, right? Because it's a positive, and bromine right here is partially negative. So he attacks right here, and you should be getting answer choice C. Now, sometimes he can attack from the back or he can attack from the front. So that's why you get an enantiomer, right? And it's chiral. So if you don't have a chiral molecule, you're not going to have an enantiomer. But in this case, this is chiral. So you would have both products, both R and S. So now we start seeing some new reactions. In this case, it is the Oxymercuration. So Hg is just mercury, and we have some acetate, right? So what it looks like is, if I recall correctly, it should look like this. We have Hg, O, C, and I think there's a double bond, right? And C, and then like 3 H's. Okay, awesome, cool. So the first thing you need to know about oxymercuration is that it follows Markovnikov. So OV and IKOV, I believe. Markovnikov, we're gonna have a heart, right? So we have a heart, and that means that we like it. So we follow Markovnikov. And what you should know is that when you have mercury or oxymercuration, you're gonna have sodium BH4, okay? So whenever you have that as a pair, here's what happens, right? So I'm just gonna show you the product, and then afterwards I'm gonna do the mechanism. It's quite lengthy, so I'm just gonna show you the product first. What happens here is that also no rearrangement. Okay. What happens here is that we have two hydrogens on this bond right here. So we have H2, and over here we have one hydrogen, right? Okay, so where should my molecule go, right? Whatever I'm going to put in, where is it going to go? Well, since it follows Markovnikov, the hydrogen is going to go over here, and then my other molecule is going to be over here, right? Okay, but what am I adding? Well, you're actually adding an alcohol, right? So that's pretty weird. What happens afterwards is that you should be having a product like this. So since we're following Markovnikov, your alcohol should be right here, right? Now this could have been a wedge as well. Now it's a wedge or a hash because this portion of the carbon is chiral, right? So what happened to your alcohol? Why is there no alcohol right there? You have oxymercuration and you have sodium BH4. There should be an alcohol somewhere. So that's wrong. A is wrong. Why is this, OH over here? That's anti-Markovnikov. That's not right. Okay? What they did here is that they put the alcohol on this side and they put a hydrogen on this side. That's incorrect. That's anti-Markovnikov. We follow Markovnikov for oxymercuration. Okay? So answer choice C is incorrect. And D is incorrect as well because you're putting your alcohol on this carbon and not this carbon. So that's incorrect. Okay? That is also anti-Markovnikov. Not good. Plus, this carbon already has a hydrogen, so where did that hydrogen go? It should only be on one or two, one of these guys, okay? So that's not making any sense to me. There's no rearrangement either, so that's definitely not D, and it's not E. So by process of elimination, you should know that it's B. But now let's go through some pain, and find out how this mechanism actually works. And to do that, I'm going to have to redraw my substituent, or my substrate, right? So here's my pentane, cyclopentane, I should say. And let's put them over here, right? Okay, so what happens here is that you have mercury, OAC, so that's like acetate. And this has a lone pair, right? Okay, so what happens is that this lone pair actually attacks this guy right there, okay? And this double bond attacks the mercury in return. Like it's like a retaliation, right? So notice that I didn't put my arrowhead pointing at this carbon, I actually pointed at the carbon that had the most hydrogens, okay? It has the most hydrogens, right? And what we get now is a cyclopentane, right? The cyclopentane, and we should have actually a breaking for this bond for the acetate, and then very weirdly, it's very common actually, this mercury is going to be connected to both carbons. So it's really weird. It's really weird, but it's true. So let's have OAC, and it's double bonded. So there's a bond right there to that carbon and that carbon. Okay, so now we have the issue. We have the issue of which green bond is going to break. Are we going to break this guy, or are we going to break this guy? So which one is going to be more stable when we break it? Are we going to make a primary carbocation? So if I break this, if I break this bond, I'm going to make a positive or a primary carbocation. But if I break this bond, I'm going to make a secondary carbocation. So which one am I going to break? Well, I'm going to break the this one, because if I break him, he's going to give me a secondary carbocation. Okay? All right. So what we have now is a cyclopentane, right? And some mercury with an acetate, right? And right here, you should have some water. So just water is just, hanging out. And he sees this positive carbocation that you made. And he's actually going to be really attracted, and he's going to be attacking it. So, what was I doing over here? This is terrible. Let's redraw him. So we have this guy and OAC. Now we have water attached to the secondary carbocation, and that's pretty cool. That's really cool. Alright. And then the OAC that left, so we have OAC, it turns out to be this one. He comes back and he actually attacks the water molecule. So he attacks the water molecule. How? Well, the hydrogen pops off and he collects this hydrogen. So that makes our alcohol. But now we have the problem of having this. Let's draw our alcohol. But then we have HG OAC. So how do we get rid of this mercury? Well, that's what the sodium BH4 comes into play. The sodium BH4 actually takes care of that mercury. So here's what happens. So we have sodium BH4 negative, and this goes over here, and then he collects the mercury, right? So that is basically how you do the reaction. Okay, so let's go over it again. First of all, the mercury attacks this double bond. He attacks where the most hydrogens are. Okay, so we have two hydrogens right there. There's only one hydrogen right there. So the lone pair on the mercury attacks the H2, and likewise the double bond attacks the mercury. So after it gets attacked, it shoots off an OAC. Okay, and so the mercury is double bonded to this carbon-carbon, right? So the mercury is attached to this carbon, and it's attached to this carbon. And I'd rather break the secondary bond, because if I break him, I'm going to get a secondary carbocation. So that's good. Then a water molecule comes out of nowhere. Well, not really, just it's there, okay? Because it's in our solvent. It's in our solvent, right? So we're surrounded by water everywhere. He comes out and he attacks this carbocation, okay? Now we're over here. The OAC that shot off takes a hydrogen away to make our alcohol. And then in the part 2, we have sodium BH4. He takes out the mercury, and we're left with an alcohol. So now we do yet another Markovnikov question, right? So now we have to react with HBr and sodium cyanide. So in the first part, which is part number 1, we're just going to do a simple Markovnikov addition. So this is Markovnikov favored, right? What happens here is that HBr breaks the bond, releasing this hydrogen. Let's see, we have one hydrogen right here, and we have two hydrogens over here. Okay, so in the Markovnikov addition, the hydrogen just goes with more buddies. He has more friends over here, and so my hydrogen should be right there. Here's what we have now, right? So now we have 3 hydrogens over here, that's implied, and we make a positive carbocation over here. That's a secondary carbocation, right? Okay, that means that the bromine attaches itself to this part, right? and it's actually, it could be a wedge or a hash because this is chiral. Okay, so let's just make it into a hash, I guess. All right, so that's good. We just did step 1. Now in step 2, we have sodium cyanide. Now sodium cyanide is I mean, it's negative, right? So you would actually do an SN2 reaction, right? So that's and it's also an aprotic solvent, dimethyl sulfoxide. You just need to know that DMSO has no hydrogens to give up, so it's going to be aprotic. SN2 favors aprotic, so for sure it's going to be SN2, right? And so what you should be having is this guy right here. The bromine pops off, the cyanide goes in, and it comes out as a wedge. CN, not CM. And we should have a wedge, or hash hydrogen. Well, A is wrong because your cyanide is not in the correct position. B is wrong because you have 2 cyanides. C is wrong because you have 2 cyanides. D is wrong because you shouldn't have a double bond. And where's your cyanide? So E would have to be the correct answer choice. None of these choices. All right. Now we have to do a reaction with T-butyls. Okay. So that's a E2 reaction. This breaks off, forms a positive carbocation that's secondary. Can we make this secondary carbocation more stable? Well, yeah, we could if we did a methyl shift. If we did a methyl shift, then what we end up with is a tertiary carbocation. Right? And we have some implied hydrogen. Well, if we want to make a double bond, we can just break off this hydrogen and then use the electrons to go over here, right? Well, actually we wouldn't break off that hydrogen, we would just make a double bond, right? So just make a double bond so that it's the most substituted. So we have a 1, 2, 3, 4. We have 4 bonds connected to that double bond, so it's very substituted, very good. Right. Now let's go over here. We're going to do step 2. Right. So now we're reacting with HBr. Okay. Well, that bond breaks, releasing the hydrogen. Where is that hydrogen going to attack? Where is it going to attack? Well, it could attack right here, and my bromine would be left over here, right? So actually, let me do this because that was the wrong arrow pushing. The double bond attacks the hydrogen, and we're gonna make a positive carbocation over here. Now it's gonna be what? It's gonna be tertiary, and it's gonna accept this bromine, right? So it's gonna accept that bromine right there, okay? And so for the answer, you should be having this. And so the hydrogen that you added is over here on this H, and then you have a bromine on this carbon, right? So that would correspond to answer choice C. Okay, so now we're doing an acid reaction with this molecule. So those are pretty hard to draw, so I'm not going to draw it out again. However, I will draw out the reactants. What happens here is that we will follow Markovnikov. So acids typically follow Markovnikov rule, right? So what I like to do first is to draw out my hydrogens. So for this carbon, we have 1, 2, 3, 4 bonds. That means that we have no hydrogens on that carbon. But on this carbon right here, we have 1, 2, 3 bonds, so that's an implied hydrogen because carbon wants 4 bonds. And that must mean that when this hydrogen breaks off, he goes with his buddy. Let's do it like this. This double bond actually takes that hydrogen. And this makes a positive carbocation on this side right here, right? Okay, and that must mean that the oxygen for the water, so this water molecule, he is positively or he's negatively attracted to that positive carbocation that was formed, okay? Afterwards, water, so let's do this. So here was it's this section that I'm drawing out, okay? So we have water, and then another water comes out of nowhere because it's in our solvent, so it's surrounding us, and he wants to take out this hydrogen, okay? Well, he takes out this hydrogen, and we're done, right? We are done. We made an alcohol. Notice that this carbon right here gained a hydrogen, and then the other carbon, the neighbor, gained an alcohol. So in total, you have OH and H. That makes H2O. So technically, we did add, we added water across this molecule. And so your answer should be answer choice 4, right? Because it follows Markovnikov. Hydrogen goes with its buddies. So the area that has the most hydrogens will accept the hydrogen from the reactant, okay? So now what is the major product of the following reaction with BH3 and peroxide? Well, this is what we refer to as hydroboration, right? So hydroboration is BH3 reacting with peroxide. And you should know that for this reaction, specifically BH3 and H2O2, they're gonna do anti-Markovnikov. So anti-Mark. What does that mean for you? Well, it means that over here we have an implied hydrogen, and we have 2 hydrogens right there. So normally for a Markovnikov reaction, your hydrogen should go over here because it has more of its buddies, right? But in an anti-Mark, the boron is actually attracted to this region, okay? So it's attracted to that region. And you should think of it as follows. You should have HBH2, right? Because, well, whenever you do the reaction, it's easier to kind of understand what happens. Technically, this boron is actually a bit positive. It's more positive than the hydrogen when it has a bunch of hydrogens connected to it, right? So that must mean that, actually, since it's negative, right, or more positive, that must mean that when this bond breaks, the electrons go towards the hydrogens, and this double bond cleaves, it breaks, and it takes that boron, right? So it's pretty weird. It's not intuitive what happens. So you should have BH2 and your hydrogen right there, right? Okay, so now what happens with the peroxide? Well, the peroxide just sees it, and all you should know is that the peroxide takes away this BH2 and it makes an alcohol, right? It makes an alcohol. And so you should not have a double bond. That's wrong. B is wrong, right? Where is your alcohol for answer choice C? Where is that? It's not there, right? Let's see, D and E. Well, why do you have 2 alcohols on E? It makes no sense either, right? And why is your alcohol on the second carbon? It should be on the first carbon. See, they did Markovnikov. That's incorrect. You're supposed to do anti-Markovnikov. So D is incorrect as well. Right? So realize that for hydroboration, you might see that on the exam, it might be saying hydroboration. If you see BH3 and peroxide, just think anti-Markovnikov. Right? So you should already know that anti-Markovnikov goes for peroxides, and they have the formula R2O2, so it looks like this. That's a peroxide, right? So it could be chlorine, chlorine, bromine, bromine, iodine, iodine, doesn't matter, whatever the R's are. If you have a pair of oxides, it's peroxide, right? That's how I say it. So peroxides, also potassium manganate, KMnO4, potassium manganate, peroxides, they are anti-Markovnikov, and that's pretty important for you to know, right? So that looks pretty good. Also, let's do BH3, right? BH3 is also anti-Markovnikov. So answer choice A would be the correct answer. Now we're doing a reaction with ethyl oxide and ethyl hydroxide for the first part. Okay, so let's redraw our cyclopentane. What happens here is it is an E2 reaction because we have heat, so E2 reaction. Also the sodium is strong, so automatically that's going to be SN2 or E2, but because we have heat, that's going to be E2 reaction. Therefore, my chlorine breaks and forms a carbocation. That is tertiary. Now we have the option of making a double bond from either hydrogens, right? So these are beta hydrogens. Take your pick. It doesn't matter which one out of the 4 you pick. You're going to get the same answer. If you pick the top ones, you're going to have to rotate your cyclohexane or cyclopropane to get the answer. So I don't want to do any rotation, like physically taking a model and then like rotating it like 60 degrees to get the same configuration for these answer choices. I don't want to do that. So I'm just going to do the bottom ones. But it's, preference for you, right? So now let's say that the bottom hydrogen breaks and give me my double bond right there. Okay, well, let's do it interior. Right, so that was step 1. Now we have to do BH3 and peroxide. Well, BH3 peroxide, that means it has to be anti-Markovnikov. Right? How many hydrogens are on this carbon? On carbon 1, there are 0 hydrogens. On carbon 2, there's 1 hydrogen. So normally you would be expecting that your hydrogen goes with this guy, but actually you should have your BH2 right here. And you already know what you're going to get in the end. So instead, you should have this right here. So we have BH2, or hydroxide. Okay, but Brian, answer choice A is clearly wrong because that's Markovnikov. I get that. I said, okay, that's cool. Well, and it's not D because you don't have any alcohol. I'll say that's valid as well. But what about B and C? Is the alcohol going to attack on the top or is it going to go on the bottom? And, we could both cry and sob and maybe hug, right? We could do that without crying, but whatever. It's OChem. But here's what you should know. This reaction right here has to be syn. It has to be syn, aka cis, to hydrogen. It has to be cis to hydrogen. Well, what does that mean? Well, it means that if I make... So, let's just say that this hydrogen right here, it, hold on, let me think about it. I get lost in my train of thought. So we formed a double bond, so it's right there. Okay, that's cool. Make a double bond. Well, it means that if I have a cis, or if I have a wedge hydrogen, or not hydrogen, but alcohol, it means that the H from BH2, right? So technically that's BH3. When this breaks, we're going to add a hydrogen. That's what hydroboration means. It means that we're adding a bromine. It means that we're adding a hydrogen to the molecule. Now, when we add the hydrogen, it's going to be over here, right? But it could have a hash hydrogen or it could be a wedge hydrogen. Well, let's say that I put my alcohol on the hash. It must mean that my hydrogen also has to be a hash. Okay? So that must mean that it must be C, the answer choice. Right? So why is B wrong? Well, you added your alcohol on a wedge. Okay, that's good. So I'm expecting for hydroboration for my hydrogen that I added over here, it should also be a wedge. So this methyl should be a hash. Well, this is wrong because you're saying that you have a hash hydrogen. So the hydrogen and the alcohol, they have a trans relationship. And that's not good. You want a syn relationship. You want to have a cis relationship for hydroboration. Now C is correct because you added your alcohol as a hash. And so therefore, when I look at my added hydrogen, which is implied over there, it should also be a hash. So they share a cis relationship. So that should be answer choice C. Answer choice C. That's good. It was pretty difficult for me to explain, but I hope you get it. Now, over here, we have what is a major product for this guy. Okay, well, what is that? Well, you could just do this. You could have a cyclohexane, or a hexene, sorry, cyclohexene. And we're going to do anti-Markovnikov. So let's see over here. There is no hydrogen on this carbon, but there's a hydrogen on that carbon. That must mean that my alcohol is going to attack the carbon with the hydrogen, right? Because normally the hydrogen goes with its buddies, but this is anti-Markovnikov. This is anti-Markovnikov. So that must mean that my alcohol goes with the hydrogen. Okay, so I should be expecting an alcohol over here, and let's say that arbitrarily is going to be a wedge. Right. So we added our alcohol, but then we have to add a hydrogen. So we add the hydrogen over here. Okay, we add the hydrogen. Let's do that in a different color. We add the hydrogen over here. Now it depends. Do we put that on a wedge or do I put that on a hash? Well, since I added my alcohol on a wedge, my added hydrogen should also be a wedge. Should also be a wedge. Now answer choice E would actually be correct. It'd be correct. Okay? So you could have added, by the way, it says enantiomer because you could have added the alcohol as a hash, and then your hydrogen would be a hash. So that would be the enantiomer of that one. Okay? But for E, you have an applied hydrogen right there. Alcohol is wedge, hydrogen is wedge. That's good. That is a cis relationship for hydroboration. So that is good. Over here, this is wrong because your alcohol was added to the wrong carbon. So that's D is wrong. Over here, you're saying that your alcohol has a trans relationship with the hydrogen. That's bad. You want a cis relationship with the hydrogen. So your alcohol, if you wanted me to correct this, you would have an alcohol on the wedge, and then this ethyl group would be hash, and that hydrogen would be wedge. Over here, you're saying that the wedge alcohol is in a trans relationship with a hash alcohol. That's incorrect. Over here, B, you don't even have a cycloalkene. Where did you get this second oxygen? Why are they double bonded? How did you get carbonyls? That's bad. Why do you have two alcohols? No, disgusting. So now we're back with oxymercuration. It's been a long day. The mercury boy. Okay. Oxymercuration. My goodness. Okay. That's great. Now, here's something that's super important for you to know. Whenever you're doing some oxymercuration and you have carbon alcohol, right? So if you have ROH, expect your final answer to have that R group. So in this case, we have an ethyl, right? So we have an ethyl. Expect in your final answer to have this. If we had a butyl alcohol, or butanol, or I should say butanol, then expect a butane on your answer. If you had a methanol, then you should have a methyl group on your answer. Are you following the pattern? Right? So this ethyl would be the R group. So you should have an ethyl on your final answer. You shouldn't have an alcohol, but you should have an oxygen with an ethyl group. Okay? So automatically D is wrong because where is your ethyl group? Also, you formed carbon dioxide. Not good. E is wrong because where's your ethyl? That oxygen should have an ethyl somewhere, right? So A, B, and C, they look good. They look good. Well, actually, C looks bad. Why? Well, why is oxygen reacting to this methyl? It should be reacting with a double bond. That's wrong. So it's either A or B. A or B. A or B. Well, we follow Markovnikov's rule. Mark, right? Mark favored. Okay? So that must mean that, well, I'm not going to show the reaction again because that's just a pain, right? But when we follow Markovnikov's rule, we say that this has 2 hydrogens right there, and this has 1 hydrogen. Well, our hydrogen wants to be with its friends, so it's going to be with 2 hydrogens. That must mean, if I can draw, that we form a positive carbocation that is secondary. So now we hook up our alcohol right there, and you would say, oh, I'm done, it's E. No, wrong. We have an ethyl group. We have an ethyl group. So now this hydrogen pops off, and he actually reacts with the ethyl, with the ethyl right there. So we have CH2, CH3. So it should be answer choice B, CH2, CH3. If I had a methyl group, or if I have methoxide, I should have this. If I had butoxide or propanol, then I would have this. Propanol is like this, and then butanol would be that. Pentanol, hexanol, heptanol, octanol, nonol, decol. You get it? So we have Lisa Simpson right there, right? I can't draw, but whatever. I'm just saying that if you have an alcohol with like an R group, then you should have that R group attached to that oxygen. So that is your answer, B. Now we have H2, and then basically Lindlar's catalyst. We have calcium carbonate, and Lindlar gives you a cis, aka a syn product. So it gives you a syn product. So I should be expecting a cis product, right? And let's see. Well, E looks pretty good, right? And we also have this guy. We have BH3 and peroxide, so it's going to be anti-mark. And you should probably do this on the exam. You should probably look at your reactants and write what I'm doing. So it's anti-mark and gives OH. So anything that doesn't have an OH is wrong. Okay? So let's see. That must mean that D is wrong because we don't have a alcohol. And this also means that B is wrong because we don't have an alcohol. We have an oxygen that is double bonded to a carbon, but that's not an alcohol either. So let's get into the reaction. Let's do this in pink. Or black, apparently. Right. So we have a carbon that's triply bonded to another carbon, and it has a hydrogen. Really can't draw. Well, we do hydrogenation, which means that it's going to be a cis product for adding hydrogens to this bond, right? So we have hydrogenation. You should get rid of this double bond, or this triple bond, make a double, and then make it cis. So it should be like, if I could draw it correctly, I probably can't. Yeah, just keep it, whatever. So it should be cis. And then we have to do an anti-Markovnikov addition, right? So here's H, and then here's going to be H, and let's see, 1, 2, 3. That mean that we also have an H right there. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we have to do Markovnikov, anti-Markovnikov. Well, where do I put it? Well, anti-Markovnikov, hydrogen wants to have the most friends. I mean, it doesn't want to have the most friends, right? So let me clarify. Markovnikov says that hydrogen wants to be with more hydrogens. For anti-Markovnikovs, we do the opposite. So that must mean that we have what? Then we have our alcohol over here. And then we put the hydrogen on this carbon. So it only has one friend. Well, this means that he breaks off. And, well, he basically makes this more negative, I would say. Well, I mean, that's not really important. What's important for you to know is that you should have your alcohol on the last carbon. So that's why answer choice A would be incorrect. Like, first of all, this isn't cis, this is cis, right? It's basically what we drew out, it's E. And where does this methyl group come from? Like, there's a methyl group and then it doesn't make any sense. It should be E, okay? It should be E. It's really late, but whatever. Yeah, so anti-Markovnikov, it favors the hydroxide, or the alcohol, I should say, on this last carbon. Right off the bat, I know which one is not correct. It's answer choice E would be wrong. You only have 2 bromines to work with. Where are you getting these 2 extra bromines? Not good. Answer choice D would be incorrect. Where is your other bromine? Same thing for C. Now, logically, let's think about it. Do I want to make a stable alkane? Or, yeah, do I want to make a stable alkane? Well, yeah, I do want to make a stable alkane. Okay. Well, why would I put bromine on the same side? Why would I do that? That's not good. If you did that, then bromine is going to be colliding with its other bromine, right? But if I put it on opposite sides, so they're trans, well, this bromine is going out towards me, and this other bromine is going out towards into the page, and so they're not colliding. And if they're not colliding, they're not doing any unwanted energy strain, and so that would be the most favorable. It would be B. Okay, so for this one, the reaction would look like this. You have H2. Well, first off, this bromine, or not this bromine, this double bond attacks the hydrides. Let's do it like this. It makes it cis. And then in the second step, Br2 is added. Br2 is added. So he breaks off, and let's see, he breaks off. This double bond can get bromine right there. So that must mean that we have this guy. Let's make him a hash. Because again, this hydrogen could be like a wedge right there. Could be. And if we're going to do that, let's do it over here. They're going to be on different carbons as well, obviously, but anyways, since the bromine was a hash, I'm going to make this bromine a wedge. Let's do it right there. Okay. Let's see, bromine, and then hydrogen. Okay. So that was pretty good, actually. Yeah, there you go. Now we have a double halide, so this could be like Cl2, I2, Br2 in this case, and we also have water. When this happens, you're going to have an anti-reaction. So not anti-Markovnikov, that doesn't happen. Instead, you're actually doing a, I should say it better, a trans relationship. It should be trans. So when this happens, you should have a trans relationship, and you should have one bromine, or chlorine or whatever, and then one OH. So 5 is wrong because you have 2 hydroxides. 4 is wrong because you have 2 bromines. 2 is wrong because you have 2 bromines. And then 3 is wrong because they're not trans. So it's going to be A. 1. If you want to see this reaction worked out, you could just skip ahead or whatever, right? So Br happens right there. This one breaks. Yeah, the bromine. Eventually, you do this. And then you have water, and it does an SN1 reaction. Very fun. Does an SN1 reaction, so this breaks off. Well, let's do it over here, just to make it obvious. This breaks off, goes here. We make a water. And then this water breaks, or this hydrogen breaks, and it makes alcohol, and it turns out to be trans. So very cool. There we go. So that would be your answer choice. Right. So, I mean, it's either or, I guess, right? Either or. It could have been up or down. I just picked upwards. I wasn't looking at the answer choice, but it's A, right? So likewise, you could have just done the bromine like this way. I don't know, like, well, I do know, but you could have just gone the down path, right? That's what I'm trying to say. It's just randomly how I did it. So it's A, right? So whenever you have a double halide with water, the answer choice should be trans. You should have one halide, and you should have one alcohol. So now what is a major product? Again, we should be having a trans relationship, one bromine and one alcohol. Okay, so B is wrong because you have two alcohols. C is wrong because you have a cis relationship between the halide and the alcohol. Again, this is wrong because, let's see. Yeah, so D is wrong because you have a cis relationship, alcohol and the bromine. Again, cis, wrong. Should be trans, should be A. Also, what happens if we had this? Would that be correct? I mean, we just did an enantiomer. Is that correct? No, it's not correct. Turns out that alcohol tends to be in the area that is the most substituted. But what does that mean? It means that the alcohol doesn't like to have hydrogens on it. Okay? So if we did this, so this is after we did the double bromine reaction. You should have this double bond takes away, and you have a bromine and a bromine. Technically, one of them should be cis or trans. It doesn't matter in this case. Well, if you want to be kind of technically correct, that would be a wedge. I mean hash, and so this would be a wedge right there. Okay? So because this hydrogen is right here, the alcohol is not going to want to be there. It's going to be over here in this region. So when this bromine kicks off, it makes a carbocation. Then the water comes in because it's slightly negative. It's going to go in here, and it's going to retain its hashedness, right? So it's going to be answer choice A. The takeaway that you should, the take-home message is that the alcohol goes where there is less hydrogen, and the bromine goes where there is more hydrogen. For potassium manganate with water, you should be expecting a product that has a double alcohol. And it should be cis. So it should be cis. Not cis to the hydrogen, but cis alcohols. So if you have a wedge alcohol, you're going to have a wedge alcohol. So this is wedge alcohol and wedge alcohol. Or a hash alcohol and another hash. Okay, so first of all, 2 is wrong because you have a metal that's connected to the molecule. Metals don't connect, okay? They don't connect. That's wrong. Where's your alcohol for number 1? Wrong. This one is trans. That's wrong. This one is also trans. That's wrong. You have 2 alcohols or cis. That's right. Answer choice 3 is right. So now you're dealing with osmium and you have like 4 oxygens. It's the same thing. It's literally the same thing. So you should be having double alcohol and they should be cis. So we should be expecting some alcohols in this region. Okay. Well, this is wrong because they're trans. Where's your alcohol? That's wrong. This one looks wrong, just saying. So it should be A. And I meant to put L. This one's a bit tricky, but here's a hint. You're going to be reacting with this region, so this guy should stay the same. He's not going to change for anything. So this could be right, could be right. This one changed, wrong. This one changed, that's wrong. Chlorine is not in this region, so that's wrong. Okay, now we do Markovnikov addition. Cl. So over here we had 2 hydrogens right there, and we have 1 hydrogen right there. So H should go with the most hydrogens. That must mean that my chlorine is over here. Now it could be a wedge chlorine, or it could also be a hash chlorine. Would that be favored? Well, not really. It's possible, but it's not true. Also, to eliminate some of the answer choices, 5 is wrong, 4 is wrong, 3 is wrong, E is wrong because the rest are wrong, so A is correct. So anyways, like I was saying, we have chlorine, hash. Well, that must mean that they're colliding somewhere. That's not favorable. So while 1 and 2 are possible, I'd rather have 2. Okay, so if you had an answer choice that was like 2 is favored, or if you had a different question that was like which one of these products is favored, I would go with 2 because you're not doing any steric hindrance. Over here you have 2 big guys colliding in the back, so they're going in the same direction, they could hit each other, so that's not favored. It's possible to do, but it's not favored. So technically answer choice A is correct, but I would say 2 would have a greater percentage of occurring. How many compounds are possible from the addition of HBr to this guy? Okay, so we have CH2, CH3. So let's see, that's carbon with 2 hydrogens. That's a carbon with 1 hydrogen, CH2, CH3. Okay. So now we have to add HBr. And you know the drill. That's Markovnikov addition. So we have 2 hydrogen, that's 1 hydrogen. That must mean that hydrogen goes in this region, and the bromine should go over here. We make a single bond. So automatically you should know that this is chiral. So you can have a bromine like this and a wedge hydrogen, or you can have a wedge hydrogen and a bromine. I meant to say hash hydrogen. Because you have 2 products, your answer choice should be B. Those are enantiomers, those are 2 different products, right? So it should be B. 27 is just a repeat. 28 is a different question. Okay, so we have to do a 2,5-dimethyl-2-hexene. Well, it says hex, so that means it has 6 carbons. 1, 2, 3, 4, 5, 6. And where should we put the double bond? Let's see, 1, 2, 3. That means we have a double bond on the 2nd and 3rd carbon. And then we have a methyl on the 2nd carbon. And 3, 4, 5, we have a methyl on the 5th carbon. Now we have to add our acid. Let's do a generic H3O. Well, what happens here, and I should write it in its molecular form. Right here. Okay. What happens here is that this bond breaks, this double bond picks up this hydrogen, and we're going to do a Markovnikov addition. So there is no hydrogen over here, but there's a hydrogen already here. Okay, so that must mean that this hydrogen pairs up with his buddy, and that makes a positive carbocation at this part. And then what follows is like a SN2 reaction, and eventually you're just going to have an alcohol over here. Okay, so I skipped some steps, but you should have an alcohol on the 2nd carbon. So you should have a 2-hexanol. 3-hexanol is anti-Markovnikov. That's not right. You should only have 1 alcohol. What it's saying over here for D and E is saying that you have dialcohol, which is 2 alcohols. That's not right. So D and E are incorrect. And why would you have an alcohol on the 1st carbon? Not good. So A is wrong, it has to be B. Now here's our old friend, right? So mercuration, or whatever, I don't know what it's called anymore, it's been so long. But what we have is that we're going to be reacting in this region. So you should not have anything there. A is wrong for that reason. Now I know that you should only have one alcohol when you do anything with mercury, so B is wrong. Okay. So now we have to do a what? A Markovnikov addition. So over here in this region, you have a hydrogen, and in this carbon you don't have a hydrogen. So therefore my alcohol should be over here. Okay, so it should be on that carbon. My alcohol is not on that carbon, that's wrong. My alcohol is not on that carbon, that's wrong. You could have an enantiomer, so that's right. Okay, and again we have some mercury and sodium BH4. Okay, so sodium BH4, where are we going to put it? We have a hydrogen right there, no hydrogen over here, so you should have your alcohol right there. Okay, so my alcohol should do that. But hey, wait a minute, we have a methyl. So remember what I told you about ROH? That your R should be on the oxygen, or the alcohol. So my answer choice should have an oxygen on this carbon, and it should also have a methyl group. Okay, so this one's wrong. Okay, this one's wrong right there, because you put your oxygen on the bottom carbon, that's anti-Markovnikov. Let's see. This one's wrong as well, because it's still the same issue. It's on the wrong carbon to begin with. Right here, where's your methyl group? That's not right. And over here, you have a methyl group, so that's going to be right. That's D. D is your correct answer choice. So there we go. Those are the practice questions for this review. We went over potassium manganate, went over bromination or whatever, and mercuration, some anti-Markovnikov reactions, Markovnikov reactions, and it's just a whole bunch of reactions. So whenever you're doing this, just go through your reactants. Oh, because I have mercury and sodium BH4, I should have one alcohol, and if I have an ROH, my R should be on that oxygen. You know, just kind of like walk step by step and you'll be fine. Remember Markovnikov, anti-Markovnikov, syn and cis relationships. And on the next screen, you'll see some, you know, like the quick concepts. And I hope that will help you. Again, I hope that you have a great day and that you do well in your exam. Remember that I love you and I'm proud of you. So take care and have a great day. Thanks for watching.